Okay, this is going to be the first series of a few videos, mostly for Baz, but I want to share this idea. We're going to do another little collaboration video and see where this goes. I have no idea where it goes, to be honest, where it's going to go, but this is the WT diagram, and this purple is a phase curve. GTSM stands for General Theory of Stellar Metamorphosis. Everybody knows that. Taylor threshold, that's where life forms up here. This is where the life-giving stars are. And in the yellow, the stars evolve too fast to form life. Now, I wanted to be clear with people, a phase curve is not something where a star moves down. And I did this quick example here. You have star D, C, B, and A. We'll call them Delta, Charlie, Bravo, and Alpha. As the star evolves, it goes down a what I would like to call, I have another page here. Did I write it down? No, I did not. Oh, wait, yeah, I did. I want to call the main line where a star moves down a transformation curve, just so we can communicate this idea. A transformation curve is the main curve that goes all the way down as the star evolves. And a transformation curve is not a phase curve. A phase curve is the purple. A transformation curve goes all the way down here. And star Charlie and Delta, they move down their transformation curve. Boom, 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 boom. And all the way down to where they die down here. So you have your dead moons. And the x-axis or the y-axis is mass. So think of these as massive bodies. So it gains mass. Something really strange happens right here. I think Daniel Archer is working on that. But then as it goes up to the blue giant stage, it starts to lose mass and heat and light. And it grabs onto a ideal, meaning ideal smooth transformation curve. Now, the reason why I say ideal is that I don't believe it's smooth all the way. Maybe a red dwarf would get an orbit around a very large, hot blue star way over here, and then lose mass really fast, and then kind of like jut down right here, and then grab onto another transformation curve and go down that way. So it can move in that direction. Or like if a hot Jupiter, like right here, is orbiting something really, really close, it can lose mass a lot faster and then jump the tracks, so to speak. So think of these as railroad tracks. It can jump the tracks and then share the same transformation curve as Charlie does. So Delta can share Charlies, Charlie can share Bravos, Bravo can become Alphas, giving they lose mass at faster rates. As well, it can't go up, so you're not going to see a random increase in mass by a lot. That's going to be highly improbable. If anything, it's going to lose mass quicker. It can jump a transformation curve by losing mass quicker. As well, D, Bravo or Delta and Charlie, those two stars move down just like this, and they can also evolve. They also evolve. One evolves slower than the other. In this case, as they move down their transformation curve, the phase curve shows that even when they are going in the same direction and they can both host life, Delta will possibly be or will reach ocean world stages after Charlie does. So Charlie will reach there first, because remember, this is years. You get older as you move on this diagram. So Delta is the slowest moving one. It's going to reach to the ocean world stages a lot slower or late than Charlie. And then if you follow down here, Bravo would reach ocean world stages a lot quicker, and Alpha would reach ocean world stages really, really fast. And being that it needs to time the host's life to create life, Bravo and Alpha, they evolve too fast because they're below the threshold, the Taylor threshold. They cannot form life because they evolve too fast. So what this means is you could possibly have ocean worlds that do not host life, sterile worlds that are just oceans. And of course, they're going to be smaller than the big ocean worlds, the soon-to-be Earth-type objects. And given the ocean world stays on its same transformation curve, it will become like Earth. And this is just a representative. Earth might be down here, Earth might be up here. I'm not too sure. We're gonna have to get more exoplanet data from the TESS Space Telescope to really sort this out. And another thing, and this is really strange, the Alpha's ocean world stages hit so early that it's literally, what would that be, like 1.8 billion years? And Delta is over here at 5 billion years once it hits its ocean world stage. So you have two objects that are both ocean worlds, but one is vastly older than the other. And that's very important because it shows us that the age difference between their stages increases as the star evolves. And that's very important to notice because it would be easy to say, oh, well, an object like Jupiter is, 450, 480 million years old. So that means all objects that are in a Jupiter-like stage are also 480, 440, 450 million years old. But that's not necessarily true because if an object in a Jupiter stage could be down in the phase curve down here where Alpha is, that object could be around 350 million years old. So it could be a lot younger than Jupiter is right now, but still be in the same stage of evolution. So it will be gaseous and have a very, very tiny iron core. And that should transition, what I'm saying is that should transition into this realization. And this is also for Baz. Iron nickel core, I just put iron. This is a representative size. Okay, so there's a lot on here. Here's Earth's phase curve. Now, mind you, Earth isn't going to go this way on the phase curve. A phase curve is just representative of stars that are in the same stage of evolution as Earth is. But if they're smaller than Earth, they can host life. They're down here. And some are smaller Earths, and some are much larger Earths. But some iron cores of larger Earths can be really big. And given where the phase curve is, can determine how large the iron core is. Now, there's going to be a lot more to this. I'm just trying to get this down. As well, when the star starts forming its iron core up in red dwarf stages, it's really, really, really tiny. And then given how much material it can deposit, the iron core will grow and grow and grow and grow and grow and grow. And eventually hits the point to where enough material is solidified and it's old enough to where it cannot form the iron core any bigger. And then eventually it just stops growing. It stops, all the mantle stops solidifying, there's no more iron to grow. So this is where the growth cutoff is. And then, obviously the star begins dying. So, but iron core growth cutoff at about right there. But of course, this could probably slope out a little bit more, a little less. I have so much fucking work to do anyways. And the objects that evolve really rapidly, this is something really important I wanted to share too. These little tiny iron cores down here, these are the alphas, this would be like the Bravo in the first diagram. See Bravo? There's Bravo. That's like Bravo. If the star gets orbit around a much hotter host, then it rips away the outer material, and it can't really form too much of an iron core. It just flies down here, and the core that it can build is just so small, and even when it does form any appreciable gravitational, even as it loses, I mean, its thick atmosphere really, really fast, it can't build that iron core as could a much larger, much gassier object, much gassier, much more gaseous object. So the iron core sort of grows, but it grows in very, very tiny amounts. The objects that can form really large iron cores, those are the objects that are, really, really big. And then you have, transformation curves that go down here and as well. See what else is there on this graph. Earth phase curve. Oh yeah, the iron core increases its size. So you could have a much larger object, but its iron core that's in the center is smaller. It needs time for the iron core to build. Think of a pearl inside of an oyster. It needs time for that pearl to build up layers, build up layers, build up layers. But then eventually it'll stop building up layers and it will cease growing and it will reach a max size. And then obviously Venus is a dead object. And that's basically it. See, max size. What was I doing right there? Oh yeah. And then some iron core, depending on where the transformation curve occurs, its max size reaches about right here. And this is where the rest of the material is solidified. It can't grow anymore. But anyways, hopefully that helps explain this a little better. I mean, it's a lot of work to do. All right, Baz. Hopefully you can make some sense of this, and if you need any more clarification, feel free to ask.